We're going to talk about Monte Carlo methods today. So just to give you the context, we're still in the space of working on variation or on inference in graphical models. And the bigger picture is that given you a graphical model, if it is of a good complexity, say with a small tree width, and or can be represented by a size, a manageable junction tree, then you do exact inference. And here are a few exact inference algorithms, right? And then, if the graph become too big, too complex, there are a couple of variational inference methods. And until now, we are here. We went through two variational inference methods. One is known as the mean field. The other is the loopy BP, right? They were each a method to approximate, to turn the inference approach into a method problem into a optimization problem. Can anybody remind us what is essentially the key idea in mean field and in loopy BP? If you get a elevator pitch with 10 seconds, maybe 5 seconds, what's the key thing in mean field? A product, Q is a product of what?
Individual marginals. Individual marginals
of individual marginals, yeah. We call it singleton marginals, right? So let's call this. So I would keep reminding you like this with little keywords and catchy sentences so that you kind of get the gist of what a complex whole business is about. Okay. What is loopy BP? Again, one sentence is possible. Yeah, you have that.
Cut off the belief propagation at a certain length. So that way, when you have your graphical model, it stops.
You're almost there. You mentioned about belief propagation or message passing, right? And we knew that message passing is correct on trees because there's only one pass between two nodes, therefore you get consistency. Then loopy BP is about you ignore whether it's a tree or not. You just do message passing on any graph. Become a local operation. On the edge, you pass this and pass that. That's it, right? So this is about MP on any graph. Okay, that's the one sentence idea behind this tool. Then I want to be a little bit more mathematical. In here, we know that inference can be understood as solving a optimization problem inside the space of marginal polytope. Right, that was kind of the key idea from last lecture. Unfortunately, I wasn't able to give it, but the TA hopefully explained it clearly. Marginal polytope are basically the convex Hall of all marginal distributions of marginal probabilities, and it is a polytope. And then mean field is about what? It's about seeking the estimation of the marginal in the space of the inner space of the marginal polytope, right? If you remember, it's defined by basically all the distributions that are factored, as you said, the product of marginals, right? And that's basically defines a subspace of all valid distributions, right? Okay. Let me just try to do this. Key equals to, right? And also this is basically is 1, and the QIK is so something like that. That's basically why it's called a singleton marginals, right? And therefore, it is a subspace of that. Because only at the corner, at the extreme point, the marginals are correct. And elsewhere, I don't know, but you can guess it must be inside the distribution because this whole convex hull is the proper space of all distributions. Then here, it is a subset of the distributions, therefore it must be inside, right? So that's the intuition I want to develop. And then in loopy BP, it's a little bit abstract because you never see that Q explicitly, right? You don't see that. All you care is really just singletons, which we call alpha I, and pairwise, which are called beta ij, right? And also there are the local consistency constraint, right? Which means that, so let's divide this. And in here, it's about alpha being, and there's a normalization constraint about alpha k equals to this, equals to 1. And then also the beta of over ij over all the j equals to alpha I, right? That's the so-called local consistency. Your pair of marginals, when marginalized over one of the pairs, you get the singleton marginal, right? So this again defines a constraint on the marginals, but you want to now estimate what's the space of that? So this defines a space, right? This also defines a space of a mean field, for example. This defines a loopy BP. What is ML look like comparing to the marginal polytope? It turns out that it is an outer approximation. Okay, it's something like that. And why? Well, it takes some intuition because again, they are consistent on the extreme point. But here, you don't actually have the proper distribution Q explicitly defined. There may be some weird construct where when you come down to a pair or a singleton, they are proper marginal. But when you multiply them together, they don't actually form the true distribution. They form something that is probably not a proper distribution. So there are instances which may be outside. Right? And also, in fact, you can use another mathematical justification. This whole thing is called a Minkowski subspace, or some kind of convex space. Okay, therefore it is the outer space of that. Okay, so there is a guarantee for convergence, but it is not necessarily in the proper distribution, something like that. Anyway, so I'm not going to say too much, repeat the lecture. It's a little bit deep, and there is a reading chapter, if you are interested in digging into the theory into that. That was actually, again, representing one of the most elegant piece in graphic model study where a heuristic, invented some years ago, later was proven to be a elegant, mathematical program where we know the properties and so forth. Today, I'm going to cover another beautiful piece of inference in graphical models, which also has a lot of theory and guarantees behind it. Very soon, we're going to navigate out of the beautiful space and into more treacherous places. Okay, so the other, you can already see, and the variational inference methods, require some mathematical technique, some skill. Okay, you need to really design, some, practice some algebra to basically infer or derive the equations. In the domain of statistics, we have some additional ideas that people used to do specific inference problem. For example, here is an inference problem. Okay, And you need to basically be able to do integrations over a distribution of arbitrary form. But here it's very easy. You have a Gaussian distribution, and you know how to do the integration, hopefully, right? But what if you have a distribution like this? It's very, very weird, of arbitrary form, okay? And how do you, define, a mean of function whose sample are coming from here? Okay? So the sample-based representation says the following. You can draw samples from all these, from this distribution. We use this representation T of Px to do that. And n can be from 1 to capital N. Okay. And then you can use this approximation That's it. You just plug in that sample into the f function, and then you sum together all the instances, and you take an average. Okay, this is a sample-based representation. Therefore, instead of manipulating this function p, you actually are keeping, such a collection of samples, okay, as the representation of the distribution. It's not explicit; it is implicit. Okay, no analytic forms. Okay, and nowadays the idea about a implicit distribution gets a little bit extrapolated and extended to broad definition. For example, in the space of we are going to learn about GAN models, the the generative adversarial networks, where the distribution at the top of the GAN model is not actually a P that is well known, as analytic form. It is also represented by some samples. Right? So this is a valid thing. In the GAN domain, the samples are drawn from a natural example, your data collection. But in here, you can also simulate the samples from distribution. So that's the key idea. So now let's see how we can maybe just walk through an example to see what issue you may run into. So here I have a distribution of 5 random variables. And how to sample? Well, it should be not too difficult. You just walk through the network. Remember, the relative graph models has the advantage of being easy to sample. Right? You sample from, say, E. This one is your first. This one your second. You just draw basically from this local marginal. Here you can see that there is a low probability of earthquake, 0.002. You draw a sample, you get a instance of a no earthquake. And for the second random variable, burglary, it's also low probability. You draw a sample, and which reflects that probability. And then given this E and B are now instantiated, you can conditioning on that and draw the sample alarm, which actually use this table. So which sample are more likely to be drawn? If you were to draw A, conditioning on B and E, what are you going to have? You need to pick the right row in this table, right? Which is now 0 and 0, meaning false and false, that's here, right? And then you draw a sample. Okay, so that's basically how you walk through the graphic model and draw an entire slice. So we call this X1. Okay, the X is a vector in this case with 5 random variables. So this is a random vector. And then you draw this. You can go on and draw 10 rows like this, 10 examples like this, all the way to, do we have 10? Yeah, okay. And then you are going to now do your inference. Say this query is about the conditional probability of John makes a call, conditioning on the alarm is off. Okay. So how do you do that? Well, by definition, it is the joint of J and A0 divided by the marginal of P of A of 0. Then what you do is to just look at all these samples. Okay, how many rows where A equals to 0? So I have this, 80 examples. Actually, 9 examples. Okay, and then out of these 9 examples, how many rows John equals to 1 and how many John equals to 0, right? So that gives you this kind of breakdown. Okay, so very easy. So inference becomes just counting numbers and then do some normalizations, right? Now, I changed my query. I still use the same example. Now my query is about conditioning on the event of A equals to 1. Okay. So in that case, we have only one such row exist. And then, computing this conditional probability of J given A equals to 1 become a little bit tricky because one of the events, John equal to 0, doesn't even exist. It has a 0 probability. The other has 100% probability. Right? So this already says you something, right? There are not enough samples. You need to draw many, many examples so that some rare events can exist. So this is naive sampling. Okay? It's very easy. Good part is that implementing this algorithm is extremely easy. But we've got to these few challenges. Okay, how to draw samples? In the previous case, it's easy, but there are some distributions which, for example, have this weird analytical, irregular form that you may be harder to draw example. Then how to make better use of the example? Not all examples are actually useful. You will see. For example, in the previous cases, we have 9 cases for some events. We have 1 cases for other events. Out of these 9 cases, well, maybe you don't need that many, right? But out of this one sample, they are not enough for certain events. And also, how do you draw enough examples? So these are the questions. Monte Carlo methods is basically a discipline that studies the kind of methods I said. And it begins from direct sampling. We saw it. It is not used very often other than pedagogical reason. We're going to study a few more kind of effective methods today. And we're going to look into rejection sampling more carefully. And then MCMC is the major dominating method people are using these days. Okay, now let's begin with rejection sampling. So suppose we want to sample from this distribution pi, okay? And there are a number of difficulties we just mentioned. Let's say the first difficulty will be that pi itself may be too difficult to sample from. In fact, how many distributions that you actually know how to sample from? Have you used libraries like MATLAB or R? And have you practiced or played with drawing samples from distributions? What distributions did you typically use? Maybe the most frequent one is the uniform distribution between 0 and 1, right? And other than that, what's next? The Gaussian distribution. And you know how to draw Gaussian, right? There is a formula there. You actually draw from the uniform and then you twist it with a transformation and so on, right? And I used to implement a few more because I wasn't happy with that very limited library. Therefore, you can sample from Dirichlet distribution, multinomial distribution, T distribution. There are a few you can name it. It's very hard to name beyond 10, basically. Okay, but in natural world, you have a lot more distributions that you worry about. And then there is another difficulty, which is that, for example, in the case of a Markov random field, you actually cannot really even evaluate the likelihood of a sample in that because the random field has this normal constant, which can be very difficult to compute. Right. So what the idea behind resampling is to use an auxiliary method Q, which could be a Gaussian, for example, could be something very simple. And then here is the procedure. You draw this one from a easy distribution Q. And then you are going to have a second step, which is to determine whether X star is to be accepted or not using this formula. This is pi prime, which is the unnormalized part of the distribution. That addresses you the problem of evaluation of probability under a complex distribution being difficult. Here, you don't have to go through that. You only go through the explicit analytical part, not the Z. And then here you have the probability of the sample under Q, which is an easy distribution, you can do it. But you also need to make sure that it defines you a proper probability of being accepted. Therefore, this whole thing has to be restricted between 0 and 1. Right? Therefore, you need to scale it with a K. Okay, which essentially makes the whole thing look like this. You have this guy, which is irregularly shaped, representing the unnormalized part of the target distribution. And then your Q times K should always be dominating the other one. Okay, and and I guarantee you, I can prove to you that once you draw a sample of X like this, it gets you to a point where all the X actually comes from P of X, or pi of X originally. How to prove that? You probably already see that. It's on my slides already. But just for the sake of having the idea more clearly, you need to now really prove the probability of a P of X star, right? Let's call it P, okay? And this comes from a Q of X. And then here I have a second probability, which is pi prime divided by K of Q of X. And this is the unnormalized part of the new distribution. I need to divide them by the normalized part. Right? And this part cancels, this part cancels. And then at the end, we need to have a K. K also cancels from out. Though you have what? You have a K prime. Right? Which is exactly right? So very, very easy to prove that the correctness of that. Now, this is our first more than trivial sampling algorithm. What's the pitfall of that? Mm-hmm.
We don't know the value of K.
We need to what?
We don't know the value of K.
You know it. Why don't know? You already have a pi of prime, which is easy to evaluate. You can find the extreme of that, and then you set the. You can compute it. Yeah.
Also, Q is 0 in some parts. I mean, like the probability of Q is very.
I can choose one that is not 0, right? Why for Gaussian, for example, it's not. Yes, it's not a big deal. What's the true difficulty of that? Right. How much? The shaded area, yes. This whole thing is going to be. And this is not the worst case, okay? I will write you a very, very bad case. For example, I have a distribution like this. And then your Q should be like that. And therefore, this whole thing will be rejected, right? And it can be as bad as beyond what you can imagine, okay? So here is an extreme example. Just for thought experiment, I'm going to use a Q of Gaussian to sample another Gaussian. You may say, why do that? I can sample Gaussian directly, but just for the sake of making an argument. This is our true Gaussian that you want to sample from. I use another Gaussian which use a different variance to sample from. Okay, and then my approximating Q is going to be different from the true P by just 1%. Okay, so this is just how I chose the Q. And you can verify to yourself because Gaussian distribution, it takes the form of whatever that is, and times the exponent of whatever, right? And it turns out that even for such a tiny, very, very slightly different target and proposal, the K turns out to be 1 over 20K. Okay, that means a huge white space exists, or the shaded space exists for to reject the samples. Okay, so the idea, the argument here I want to make is that in high-dimensional space, here, why it is becoming so extreme is because the dimensionality is 1,000. In high-dimensional space, even the target and the true distribution can be very similar already by looking, okay? But still, the volume of these two distributions can be very, very different, and you end up wasting a lot of samples. And there are some ideas about doing adaptive rejection. For example, I can do a piecewise, kind of a distribution like this to just closely envelope the target, but these are very cumbersome. Okay, so in a nutshell, reject sampling is okay, but it's not very efficient. The next idea is known as importance sampling. There are two versions of that. Begin with the unnormalized version. Again, let's assume that suppose sampling from P is very hard, but for the time being, let's assume that it is still easy to evaluate. If I plug in AX, it is you can calculate the probability. Not worry about normalization constant for now. And we want to use a Q in a simpler case. Here I'm going to use a slightly different formula. I want to make an assumption which is easy to satisfy, which is called the dominance. I chose a Q such that Q has a non-zero mass whenever the original target distribution is non-zero. Then we can assume this a new sampling scheme which has the following form. I sample the X from a Q. I'm going to compute something like a weight, which is the ratio of a probability of X under P and X under Q for the M's example. Okay. And then I'm going to basically use the XM and the weight M as a pair, okay, to do whatever operation. So for example, computing the mean, okay. And this equation shows you the correctness as well. Basically, if you want to approximate this integration with sample, and what I do is to plug in this Q upstairs and downstairs so that you can see this explicit form of the ratio. And this is basically the W, right? And from here to here, I replace the integration with now samples so that they sum, and then you can see that I have this weighted sum of the examples. Okay, so that's a new algorithm where every example is now used. They are weighted, therefore you don't throw them away. Okay? Very trivial, right? Of course, it's quite intuitive. And what's the problem in this algorithm?
Q is too small and P is too large.
Okay. Yeah, you're talking about the value of our sample. Yeah, but at least we are getting closer. We're getting a little better. Originally, some sample has a 0 value. Now it has some value. Okay, not too bad. So let's worry about that a little later. But remember, I still have this computability under P that is not taken care of. Right? For Markov random field, this algorithm doesn't work. So the next step is about how to get this incomputability part taken care of. So in this case, we rewrite, the distribution P to be P prime divided by alpha. Alpha is the normalization constant. It turns out that this alpha can be obtained from the samples as well. Okay, and here is how. Here's the formula. You can see that once you define the ratio to be the ratio of the unweighted part versus the probability under Q. Okay, remember this R is different from the previous W. Okay, for a reason. W is the true ratio of probability, and here the R is the unnormalized probability divided by the true probability under proposal. Okay, and you take a expectation of the R, and through this derivation, you can see that actually E equals to the alpha, to the normalization constant. Therefore, you do have the normalization constant. Okay. So what you need to do is to now, slightly change the formula, right? The computation of the expectation now, are making use of the unnormalized ratio, and pull out the normalization constant in here, which we know how to compute. Okay, yeah, and then after some rearrangement, you get down to this equation. Okay, which asks you to not only do weighted sum of the original function for sample, but also you need to do another round of normalization. Therefore, this part becomes the normalized importance. Okay, so procedurally, you need to do something a little bit differently. In the previous one, the unnormalized part is a typical online algorithm because every of this weight is available the moment you sample the example already, right? But this normalization constant is going to be available only when you sample enough and decide to use them as the normalization. Therefore, you first choose n, which is the number of samples that you want to use, and then you are going to sample the x all the way to xn. And then you also have the r all the way to rn. And then you compute the alpha, okay, with the sum of ri. And then you compute the weight, which is ri divided by that, right? And then, you are going to have these weighted samples, and then you do the summation. So that's a procedure. It's a batch algorithm rather than an online algorithm. But you can have this rolling kind of batch using a sliding window technique, right? After you finish the first 1,000, you start to, have the first window, and then you move the rolling window. Say every 10 new samples, you recompute that. That's doable. Okay. All right. So now we have a few algorithms which at least make use of every examples already, and evaluable under complex distributional forms already. Now, to address your question, and why it becomes a concern. Why, for example, low weights? He correctly points out that some samples may have low weights, some may have high weights. But what's wrong with sample having low weights? It means that it's not important, right? So unimportant examples having low weights is justified. We want that to be had that way. So what's wrong with that? So here I have a kind of a weird example where exposes the risk. Okay. So basically, one of the major kind of practical need for sampling algorithm like this is that you need to know, because the sample can go continuously forever, right? You need to know when to stop, and you need to have a criteria to determine that, hey, I'm doing good enough so that I need to stop. So what does it mean by good enough practically? So for example, you do this sampling scheme, you sample to capital N until 1 million already. How do you decide you don't want to do that anymore? What's your heuristic?
I mean, if you're doing it in an online manner, what's the end?
Whatever, online, offline, what you name it. I'm just asking very, very high-level question. When do you stop? Just like running your EM algorithm, running your K-means algorithm, when do you stop? Because the algorithm itself doesn't ask you to stop.
The delta of change of your expected values.
Right. You need to kind of set some internal monitor that if something keep changing, you need to keep doing it. But if something stop to change, then you know that doing it more doesn't cause any difference. It didn't stop, right? So here, because you are computing this guy, and if this guy, after you have one more example, it doesn't change anymore, then you stop, right? So what does it mean by it doesn't change? It means that the new samples are contributing very low variance of that, right? Okay, so let's see what can happen if you have what the sampling scheme we told before. For example, let's say you have okay, maybe this graph is too clean. I will draw another example. So I have some kind of a weird distribution like that. Okay, this is P. And I have a function that I want to estimate. Maybe this is a curve, something like that, F. I have a proposal distribution Q. And because I don't see the true distribution, remember, it's a high-dimensional distribution, which is not plottable. Right? I need to have a guess. Unfortunately, I guess the Q, I will choose another color, I guess. Does it allow me to choose? Okay. So let's say I have a distribution like that. Okay. And then what do you have? I have a low mass in here and in here. Then you will be drawing a lot of samples from here, right? And some samples from here, lots from here. Yeah, a lot from here, they will all have a low weight because, we are talking about P over Q, and this P here is very low, right? And occasionally you will have a few one in here which will have high weight, but because it's so rare, it's very hard for you to draw samples from here. So you can imagine a scenario where you draw a lot of samples, mostly from here, and then the estimation of f of xi or x stars will stop changing. Basically, they're tired of seeing bad samples. They don't just move anymore because they are all the same, right? So you are going to get into a low variance kind of estimation, even though your sample are not coming from the right distribution area. Right? So that's actually a real risk that people practically observed. It can happen very often in high-dimensional space. Okay? In a sense, you're stuck into a local kind of estimation and not going out. Okay, that's where we need to do something a little bit differently. Sorry. Sorry, I shouldn't go from the start. Okay. All right, so this is the argument I just made. Solution is the following. We have two possible solutions. One is, of course, to use a heavy tail Q. For example, why don't you choose a Q like this? Then I goes to the problem of having a lot of wasted samples, right? The other idea is about the weighted resampling idea. Okay, remember that we have these weights, right? And these weights are used to evaluate every examples in the past. But here I could have a new idea. I'm going to now stop using all the previous examples, okay, weighted by the weights I just got. I'm going to do another round of resampling. Okay, I'm going to resample from here. Here I have a discrete kind of set, and I'm going to just keep sample from here. You can imagine that if I draw samples from this sample, draw samples out of samples, okay, and if some samples have a higher weight, okay, just by luck, they have a higher weight. Maybe in the case here, you happen to have an example in here once, okay. By weighting globally, they will be, suppressed. But now I'm taking special attention to its weights, and I resample based on its weight. I have a chance of having a better weight, having it draw again. So in a sense, I began from this originally weird distribution, and I draw samples like this, each with weight. The weights are like this. Okay. It turns out that here we have a high weight region. Here I have a low weight region. And then I'm going to redraw samples. Okay. And then this example will have high probability of having multi draws. And these examples will have a probability of low draws. Therefore, this low probability area will get now suppressed, even though originally it had many samples, but it will be having a small chance to be redrawn. Okay, and I reshaped the algorithm. So this is called weighted resampling algorithm. Okay, all right. So that's all about what I want to say in Monte Carlo. There are a few other methods which I put in the supplementary, but they are kind of similar to each other. And the main issue is about how to sample easily, how to make more effective use of samples, and so forth. And there are some fundamental issues people are still not happy about. So the weighted resampling is kind of letting you to reshape kind of the proposal a little bit. But remember, it is not an online algorithm. Okay, you have to basically keep, say, 1 million examples in your storage and redraw samples from there, which may give you 10 million, and you store it, and then you compute, and then you see how good it is. And if no good, you need to do it again. In fact, you have to do it again because you need to see whether the trend is converging or not. So offline algorithm is not very, very handy, okay, for in practice. But online algorithms have the nice property of that you don't have to remember examples. You can throw them away. So therefore, there is no storage cost. And also you have this rolling estimation that every time you can monitor the convergence real time. So there are some advantage of that. The only problem is that we don't like the queue, which causes a lot of problems. So, and the part of the reason the queue is awkward is because it's a fixed proposal that you cannot change situationally. If you happen to have a very good sample, for example, just by pure luck, for example, if in this queue you have a good sample coming out of here, which matches the P very nicely, you don't have a big chance to see the good luck again, in your next 10 or 20 examples, right? But if you are willing to now move this queue into this direction to center here, then you are better off, right? So this is called an adaptive proposal, which suggests the idea about kind of using a changing queue. So here is basically the big idea behind what is known as the Markov chain Monte Carlo. Okay, so suppose that here is basically the important sampling or related whatsoever with a fixed queue, which you can see the problem, right? In this case, it's kind of almost hopeless because it's too kind of extreme in terms of mismatch. Therefore, however you reweight it and resample it and so forth, it's very hard to cover this part. The MCMC is more like a adaptive. Even if you get a sample in here, which is still kind of the value in the P, but you were able to move the queue a little bit so that its tail started to cover this part. Okay, and then you can hopefully, move into the right direction more quickly. So let's see how to realize this idea more formally. Okay, the first algorithm is known as the Metropolis-Hastings algorithm. Metropolis-Hastings are two scientists, I believe in Los Alamos or some nuclear weapon lab, and their goal was to compute again, the energy discharged out of explosion, something like that. Okay, and computing the energy states of a nuclear material is very difficult, as we see from the easy model. Therefore, they want to use sampling algorithm to do that. I believe one of the person is a real scientist, the other is a manager. So good to be a manager, to lead a few scientists, to put your name on that. So here is the idea. You are going to use a moving distribution Q, which is defined as the conditional probability of the sample given the immediate previous example you draw. And then you are going to accept this new example with a acceptance function, which is defined as this. Okay, it's the minimum between 1 and also a ratio, which is in a sense, it is the ratio defined by two types of importance. This importance, P of x prime divided by Q of x prime given x, is the importance, the old kind of definition of importance using this Q of x prime given x as the proposal. Right? So in a sense, you are moving the importance of moving from x to x prime. And here you have a inverse importance, which is the importance if you move back from the new example to the old example. Kind of intuitive, right? Or, you go forward or you go back. And then, if, this part gives you a number of less than 1, you basically are going to be, accepting the new example based on that. If it is greater than 1, you just accept that. Okay. And it turns out that this algorithm, will ensure the following nice property. After you sufficiently sample many draws, then eventually your X will be coming from the true distribution. Okay. Here we don't have a proof yet because in our importance sampling proof and reject sampling proof, it's very easy. You plug in the Q, and and then somehow they magically cancel each other, and you get the P back. Right. In here, the Q is moving; it's changing in every sample. Therefore, that technique doesn't work. Okay, but we still need to have some guarantees, and we'll see in a second. So this is just an algorithm that you can implement for any distributions of Q of P, and here is kind of a simulation about how the behavior look like. Okay, so remember we have this acceptance ratio defined like this, and you initialize from somewhere. Okay, you start also with a very bad Q, okay, which is covering just one of the modes inside a complex target. And now you have x0. You are going to draw x1 conditionally on x0 using this distribution. This distribution is basically, again, a very bad kind of distribution centered on one of the modes, and your second example, your first new example, come from here. You accept it, okay, and because this number turns out to be very good. Okay. And then you are going to anchor yourself in here, and you draw from this distribution the second example. And with some good luck, you get an example in here, which gives you a low probability under the proposal, but a high in the original. And let's see you accept it or not. Well, through a test, you actually accepted already, okay, through some formula in here. Okay. And then you are going to now conditioning on the x2, okay, and define this new proposal here. And you are going to use this as the proposal. You draw x3. Okay, and this x3, you draw a new x prime. It's not qualified to be x3 yet because we haven't decided it's accepted or rejected. So x prime. X prime is in here. Well, in here is a tricky position. It is high under the original probability, under the proposal, but low under the original. So it was rejected. Okay. Not always rejected, but at least by chance, by a bigger chance, it's rejected during this. Then what you do is to now, reuse the previous example to make it x3. You have two instances of this position. Okay, so okay, and then you are going to use this proposal again because you are not really making progress in the previous example. Therefore, the proposal distribution Q dependent on the previous example didn't move. But this time you have some better luck. You start to find a sample from the tail in here. Well, you may ask, why not here? Yeah, it's possible as well. If it's in here, then just move on and sample more, right? So now it's in here. And in here, it has a low probability under the proposal and a high under the target. It gets accepted. Okay. And in that case, you were able to make a big leap, of moving the proposal that start to cover more into the new mode in the target distribution. Okay. And that's basically how it works. Eventually, this Q of P prime, Q of X prime given X is moving back and forth to swap, it's like almost like a radar kind of swiper, for all the modalities in a complex proposal, and you are hoping that eventually it will leads you to X coming from the true X. You have a kind of a chance of covering everywhere. Okay, so that's how it works. So let's think about a few theoretical issues in here. First of all, from a practical point of view, people always do the following. For example, there is a period called the burn-in period, which is the first couple of thousand examples or samples you draw, and people typically discard them. Okay, why? Well, kind of intuitive, because we already see the early examples are usually bad examples. They're not coming from the true distribution, right? Only when you reach enough kind of samples, they start to move back and forth very, very nicely and in a balanced way. And therefore, it's more likely to harm from the true distribution. Okay? So basically, this means that these examples of n too small are not coming from P of X, in a sense. Right? Although this exact threshold isn't known, but you can make a guess. And why this procedure is guaranteed to converge to Px, we need to study that. And what's the connection between the Monte Carlo and the X? No, well, that's actually, the connection is that you need that kind of concept to prove the convergence property. So let's look at what is a Markov chain. Right? A Markov chain basically is a sequence, is a property underlying a sequence of stochastic instances. Right? And in particular, first order Markovian is giving you this property of the present is independent of the past, given the future is independent of the past, given the present. Therefore, this long conditional distribution, conditioning on the whole history, is going to be only conditioning on the immediate past. Okay, so we actually knew that from our graphic model of HMM already. So let's call this conditional probability of the next example, given the immediate previous one, to be the transition kernel. Okay, and also remember that here, when I say X, this guy can be a singleton. It could also be a vector of random variables. That is the entire set of draws from a whole graphic model. Okay, so it could be something like this. And let's make also another convenient assumption, which is called the homogeneous MC property, meaning that every time this conditional distribution, the formula didn't change. Okay, of course, the actual number changes because you are going to plug in different examples, but the form isn't changing. Okay, in a sense, the way the future depends on the past isn't changing. Okay, so to make that more explicit, I introduced this notation called kernel, which is also known as the transition kernel. Okay, and then let's define a few concepts. We need to define a distribution over state, okay, at time t. Because now at every time point, we are not just worried about the value, the correctness of that sample. We're actually concerned about whether that sample is coming from the correct distribution. Okay. In MC, remember, by consoling Q and so forth, we know that every example comes from that distribution, target distribution, right? But in here, you don't have that guarantee. The chain Q is moving, it cannot be canceled. Therefore, you want to monitor at what time the sample comes from the right distribution. So therefore, we define a time-dependent distribution of the states pi of x at t. Okay. And then we need to define how such distribution can change over time because of our procedure. The procedure is that you draw a sample from a distribution and then you transition using a kernel. So in a sense, you start from distribution, you draw a sample from, you make a transition into the next step. And what is the next distribution look like? Well, here is how they look like. Okay? You basically are going to marginalize out the previous previous states, because you shouldn't assume basically it depends on a particular position in the previous time to move to the next. It should be coming from any position, right? Therefore, you margin them out. And then after this, you time a transition probability. What's the next state? So that gives you the equation for transitioning from one distribution to another distribution. And we are hoping that this pi of 1, pi of t, and hopefully pi of capital T will be close to p of x. That's the hope. Now let's see, can we establish that or not? Okay. Then there is an important concept called the stationary distribution. Stationary distribution is a intrinsic property of the transition kernel. Okay, meaning that there may be a point, or there may be a distribution, okay, in which you have this property that the same distribution transitioning through the kernel gives you back the same distribution. Okay, this is called stationary. Okay, and in the mathematical algebraic form, this is a vector, and this is this one can be represented as what? A dot product, a left product of a matrix versus a vector. Right? Because here, if x is discrete, for example, then this transition is just a matrix. Right? So what does this look like? Right. So in linear algebra, this kind of corresponds to the eigenvectors of a matrix. And some good matrix have eigenvectors. Not all matrices have eigenvectors. You know all that, right? Right. So that gives you the hint about how to prove the existence of the distribution of the stationary. Okay, and therefore that suggests not all the transition kernels leads you to stationary, but if you choose the right transition, you may have a stationary. And stationary is important because you can kind of guess if a convergence or a to the right distribution happens. It has to be the stationary, because once you are in the right distribution, you don't want them to move out, right? It's almost like you are slipping from the wrong distribution to begin with. Once you are locking in to the right distribution, you will stay there. Therefore, the target distribution ideally should be that stationary distribution. Right? And therefore, you need to engineer a transition kernel that allows such a stationary distribution. Okay, so with all that, you can start to kind of connect the dots. Let's review a few important concepts which says something about how this T look like. Okay. One thing is called the irreducibility, meaning that from any state X, you can move to any other states with a non-zero probability in a finite step. Okay. That kind of says a property of the transition kernel. Okay. Somehow you can kind of navigate through all states and move from anywhere to anywhere else. And that actually is good because you now have no unreachable parts in the state space. You can cover that. That gives you the safety of having, you are able to achieve any target distribution, that even you don't know, because it allows at least a non-zero probability of anywhere. The other one is called the aperiodicity. It says that the MC, the Markov chain, is aperiodic if you can go out of states and come back, okay, at any time. It basically also says that you don't have to go through some kind of circle to come back. You can directly come back in one step, okay. So that also says something about the T transition matrix. It's kind of, in the symmetric kind of entry for I to J, J to I, there should be all non-zero, right? And then agordicity. A MC is agordic if it is irreducible and also aperiodic. Okay, so these two properties combined alone is known as agordic. And agordicity is very important because it tells you that you actually can reach to the station distribution no matter what initial distribution you actually have. Okay. Okay, so that's pretty much the key properties that you need for the transition kernel to allow starting from anywhere and converging to the distribution or the station distribution. Okay, it doesn't say which stationary, whether the stationary is your target or not, but at least it tells you that in this Markov chain, you can start from anywhere and converge to somewhere and then stay there without any change. And that's guaranteed by the T itself. How to prove that? Well, here is a very simple proof using the property known as detail balance. The detail balance is actually guaranteed by the agordicity. Okay, and in detail balance, you have the following property, which is that you can establish this balance, okay, from one state and another state. You can transition it back and forth. Okay, the probability of x prime to x is the same as the probability of x to x prime, based on a transition kernel. And you can show very, very easily to yourself that once a detailed balance exists, for a Markov chain, then they will always have a stationary distribution. Okay. I'm not going to walk through the proof. It's pretty explicit. So then, what do you have? Basically, it amounts to constructing the right T, okay, so that it has a detailed balance property, and then you are going to converge somewhere, and hopefully you can establish, through the formation or design of the T that it converge to some distribution like P that you actually like it to converge to. So that's why you get this very interesting Metropolis-Hastings algorithm, where the transition kernel is defined by the proposal and also the acceptance formula that we just talked about. Right? Remember, A is defined as the minimum of 1 and also the ratio of importance. right? And you can show that in this proof, which I don't think I need to go through. It's pretty trivial, that when detailed balance is established, your equilibrium distribution is actually the target distribution. Okay. So the idea is that you basically want to design a T, and using what? The T must use a Q, which is our proposal, and also A, right? And in A, you fold in the proposal, the target distribution P in certain way. In our case, it is the minimum of 1 and also the ratio of importance, which contain that component of P. And then all of a sudden, your detail balance is realized on P. Okay, it's kind of magical. Yeah, very, very easy mathematics. But that means you can start from anywhere, x0, using the transition kernel, okay, as designed in here. And then you are guaranteed to converge to P at the end. Okay, so that's basically the theory behind MCMC. So it's called the Markov chain Monte Carlo. It is a Markov chain because you keep drawing samples. It is a Monte Carlo because you keep drawing samples, but it is a Markov chain Monte Carlo because your way of selecting or designing the proposal and also picking the acceptance is using the Markov chain property, okay, among all these samples. Okay, so again, every algorithm has some caveats, and here, I mentioned a few. There is a dirty art involved in how long you burn. And then also there is some kind of cost of computing the A of X, which is a little bit tedious, and it costs you very often rejection as well. Right? People don't like it. So I'm going to show you with the remaining 10 minutes another algorithm called Gibbs sampling, which overcomes some of this idea. Again, it's a very, very easy algorithm. Remember that when we assume our sample X, it's actually in most cases, a random vector, right, of a whole graphical model. So it's basically about x1 all the way to x capital K, let's for example. And imagine that these K are the nodes in a graphic model, like LDA model or hidden Markov model or whatever. So our goal is to draw this X from P. And we know that in Metropolis-Hastings, we're going to use a proposal of Q, which allows you to draw a slice and then do the test of the whole thing. So here, Gibbs is a little more kind of nuanced idea, which talks about a particular Q. Okay. So here's what I'm going to do. I'm going to start my first example by leaving this open, and I copy okay, this is my basically next to be example after this. So let's call this x0 and call this x1. This one is to be filled in. Okay, so I use another color. Oops, sorry. So I need to fill in basically this x of 1 time 1 and dimension 1. What is that? I need to draw that sample. So I assume that I'm going to draw that from a conditional distribution of P of x1 given x not 1. Okay? And because these examples are all observed already from the previous example, I'm going to keep that and move them to here to be conditioned on. And I draw this new dimension. So I've plugged in with x1 and this. And these are all 0. Understand what I mean? Basically, my new example is all the same as the previous one except one dimension. Okay, and that one dimension is drawn from a conditional of the remaining dimensions from the previous example. Okay. Now I'm going to draw x2, and I'm going to now just basically take this out and make it a new example. Okay, and all the remaining guys are still 0. And x1 is what? Is from time 1, right? Because I already got it in here. It's copied from here. So you can see there's a tiny difference now. I have suddenly 2 dimensions now, superscribed by 1. Okay, and the remaining ones are superscribed by 0. So you can imagine that after some k steps, I'm going to get to a vector where x 1 and xk all have a superindex 1. So I finished basically the whole kind of slice of vector. Okay, so this is basically keep sampling. Every time you are going to make use of the previous example in such a way that you swap one dimension and the other dimensions are all copied. Okay. This is just a special form of the T of x prime given x, right? Which is super redundant in a sense, in using the early examples. Okay. And that brings us to some additional technique to make this process easy. Remember that we need to use this on and on to draw the next example, right? And in our graphic model, we know that one random variable in the graphic model given the rest can be simplified with the Markov blanket, right? Therefore, this one becomes this one. Therefore, in GIP sampling, typically it is very easy to draw an example using the Markov blanket idea. Okay. So that's one convenience. GIP sampling is very easy to sample from. And I have a few examples. I guess for the interest of time, let's skip that. You can walk through yourself how to practice this Markov blanket trick. Did I actually? I meant to say one more thing. Yeah, I will say that later. I think somewhere there is a proof of the acceptance rate. Maybe it's later in the slides, but we'll see. So this is another example, the LDA. Remember last time we used variational inferences, which I don't know, how do you feel? That was the first version of proxy inference for this model. It's kind of complicated, right? If I didn't tell you the equations of all this variational approximation, it may take you a while to derive that, right? Okay, so Tom Griffiths and Mark Steyer, they actually had a different idea about the same year, which is called collapse skip sampling. So basically, they identified that the only interesting thing in this whole model maybe is only this z. I sample that. I can get the estimate of that. Then I can recreate the pi's and betas just by playing with, because z is basically the counts of a label under a topic, right? Once you collect this indicator for all the documents, you can compute the frequency of topic, the frequency of words, the words under topic, and so forth. So they decided to sample to estimate only z. And then for pi and the beta, the word frequency, for every document, it's not known. But remember, this whole distribution is conjugate. You can integrate them out. Okay. Therefore, it is actually easy to just express the conditional of z given all the other z's and the words using an analytic form with the beta and alpha all integrated out. And this is basically the form look like. It's actually very, very intuitive. You can see these are the document topic term, which basically, remember this is the hyperprior of the topic weight prior. And these are the number of times, a particular document appeared in a particular topic. And this is the weighted normalizer. And in here, the betas are the prior, the hyperpriors, the dirichlet prior for the word frequency under a particular topic, right? And here are the counts of the word frequency under a particular topic. And here are the normalizer. So all these n's can be actually computed from the z's that we have so far, plus the words. Right? So this is a very, very easy equation. And then once you have this, what you can do is just to go very robotically the following. You just keep this tally of the z indicators for every word in every document. Okay, and then every time you pick one of them to be sampled from, conditioning on using this formula, conditioning on everything remaining, all the other counts. Okay, and therefore you draw a new number, and then you pick another indicator, which is word and the document specific, and then you use the other counts, which includes the old count here plus one new count you just sampled from, and draw that, right? And then you just keep doing this, right? Using this formula is invariant. You can just, the only thing changing is the n's been changing, right? So at the end of the day, you can basically run through the iteration, and these are basically the so-called topic word indicators, right? So it's a very, very trivial algorithm. It's beautiful, really, really simple to implement. And that's Gibbs sampling. That's one of the best examples of Gibbs sampling in solving, a otherwise very challenging problem. Right. Okay, so I have 1 minute left. I have a good piece of news, to conclude. If you plug in, this transition kernel, which is the conditional of a single random variable given the rest, okay, in the graphic model, it turns out that your transition probability A, or your acceptance rate of A becomes 1. Every example that you produced will be accepted. That's another very, very good news. So you have really now double down the whole case, right? You have a very easy proposal to sample from using the Markov blanket idea. And then you have a 100% acceptance rate of all the samples. And that gives you basically the nice Gibbs sampling algorithm. Okay, I think it's good time to stop. In the remaining few slides, I talk about some practical issues about MCMC, such as how to diagnose convergence, how to assess the quality of examples. We may say a few words in the next lecture, but you can go through that by yourself. It's pretty straightforward.